In today's video, we're going to be understanding the difference between weight and mass. Mass is the matter or the amount of stuff that's inside of you, while weight is the gravitational pull on you. Us humans typically get the idea weight wrong because when we weigh, we're actually just finding out the mass of ourselves. For example, if we were to throw ourselves out of space, our weight or the gravitational pull on us will be weightless or zero, but our mass would continue to be the same because we still have the matter inside of us. So basically, depending on which kind of planet you are on, depends on the kind of gravitational pull the planet has. Okay, so let's try some real life examples. Let's say you're 50 kilograms, and that's how much you weigh on. That's how much your mass is on Earth. If you want to find out what your weight is, then we have to multiply your mass times the force that the gravity is pulling on you, which would be 9.8. So we have to multiply 50 by 9.8, and the answer is 490. Also, we use Newton after a calculation to express the weight. This can also be abbreviated as N. So your mass would be 50 kilograms, but your weight would be 490 newtons. This would be different now let's say you were to take your same body, like 50 kilograms, and you were to move that to the moon. Well, on the moon, the gravitational pull is less than the Earth. Hence, when you walk, it always feels like you're leaping. Alright, so on the moon, you actually weigh less than what you would on the Earth. Here on the moon, the gravitational pull would be 1.6 instead of 9.8 like we have on the Earth. So we have to multiply, just like we do on the Earth, your mass times the gravitational pull on you, which is 1.6 on the moon. We multiply that, you get 8.5 newtons. If we were rewriting this, it would be 8.5 N. Alright, so we have a bag of chips over here, and let's say it weighs around 20 grams. Is this the weight, or would it be the mass? If you said weight, you're wrong. It's actually the mass. Because like we've been using earlier, we used newtons, or N, abbreviated, to describe the actual weight, and mass as in for grams, kilograms. In the US, they use pounds, and so on. Mass is different from weight because when we look at the definition, what happens is that weight is actually the gravitational pull on you, while mass is the amount of matter you have. The matter will not change. However, depending on where your current location is on either planet, that the weight will change. Mass cannot be zero because if your mass was zero, then you'd be nothing. And weight can be zero because if you were to go outer space, you'd be weightless, hence zero. So it's possible for weight to be zero. The unit of mass again is kilograms, grams, pounds, ounces, etc. While for weight, it would be newtons, or abbreviated N. So in our Newton's second law video, we stated that F, or force, is equal to ma, or mass times acceleration. Well, similarly, we have created a similar formula where W, or weight, is equal to mg, mass times the gravitational force. Hence, that's how we find our weight. Okay, so gravity on Earth is consistent in all places, hence our weight doesn't change wherever we go. And thanks to Newton's second law, we were able to find a similar formula to calculate the weight. So let's take this Lego minifigure over here. So let's say he was on Earth. He would be weighing, let's just say, 490 newtons. Now let's go to somewhere like Mercury. Oh my gosh. In Mercury, what happens is yours would actually be 3.59 gravitational pull. So it would be, as per the formula, his weight would be mass, or 50 times 3.59. And let's say he was to move somewhere like Saturn. If he were to move to Saturn, he would have to multiply his mass, which would be 50 kilograms times 11.08 per second square. So in this kind of demo conclusion, we can state that the smaller the planet, the smaller the gravitational force. Hence, he won't weigh that much over there. However, if we were to take a bigger planet, then the person will weigh more over there because of their higher gravitational force. Let's do another demo with these two balls over here. So we have this one and then we have this one. This is a rubber while this is wool. Now, obviously you can tell rubber is much more heavier than wool. Hence, we say, instead of saying rubber has a higher weight, we say rubber has a higher mass than wool. So we will drop it on the ground. We will check in 3, 2, 1. Because this is bouncing because it's rubber, but we can easily tell that they both drop in the exact same time. So basically, this is what we're trying to prove over here, is that it doesn't matter of your mass. What really matters is the gravitational pull that it has on you. Because Earth's gravitational pull is the same on every object, it'll literally fall down at the same time. Now, some questions would be like, how come let's say I'll take this ball and I'll take a feather. The feather will obviously take time while the ball wouldn't. What's the difference? Alright, so the reason why the feather takes a much more longer time is because of the air resistance in the air. Because of that, it's slowing the feather down. However, if we were to have an experiment where there would be no air, then it would fall at the exact same time with the exact same gravity. This is all about the difference between weight and mass.